Okie dokie. I forgot to bring my my equipment for the teaching system because I had it with me to India, but luckily I've got copies of enough of most of the material, equipment that I can move forward. So I think everything's working. What I wanted to do is go through a little bit what's been passed out in the way of homework, and then I guess you guys had some kind of meeting last week or an optional exercise class last Tuesday. Is that correct? A week ago. How many showed up? Okay, and that was about which problem? Two? One? Okay. And was everything cleared up in terms of what and how? No. Okay. So we can take questions on that, and then problem or homework 2. Has anybody taken a stab at that yet? You people? Okay. And we can also talk about questions related to that. To make sure everybody's kind of on the right track in terms of homework. And then if questions dry up and everything becomes crystal clear within the 2 hours, then we'll either start on the next topic or we'll polish up a little bit the material that was covered through the videos. How should I ask this? How many have viewed all of the videos you're supposed to view? Now don't be lying out there. Okay, so there's some hands. Okay, so there's enough there that those who have reviewed the videos can maybe pose some questions if there's some things that are unclear to the living Curtis instead of the electronic one. So today's kind of 2 hours of catch up. And like I said, if you guys dry up with your questions and comments and everything else, then we'll just kind of push forward. But in reality, you've had more videos required than you actually have time, hours, official hours. So I don't want to overload you with new material. Basically, the problem, homework 2, is on flash calculations and separator calculations. And so having a little time today to maybe clarify on that's fine. We don't need to cover more material, but like I said, instead of us all going home, we'll go ahead and at least introduce the next topics. Did the books come to the bookstore? Yes. Okay, I apologize for the price. I don't get any of the money if that's any consolation. It's more expensive. I think it's not quite double the price if you ordered directly from the SPE, but it's less hassle, I guess, to go over and buy it at the bookstore. How many? Was there plenty of copies that looked like? Yeah. Okay, so let's see here. And then I noticed that there was not a what do you call this thing here that kind of where you have a dialogue going on with questions? Where's the discussion here?
Homework problem discussion Q&A.
This one here, homework problems discussion, part 1, 2. We got to. So we don't have anything on homework problem 2, right? Is this one here problem 2?
They didn't.
But that's the actual problem, I guess. Okay. So there's not a discussion started there. All right. So let's start with the homework. Problem 1, I'm not going to spend a lot of time on that, but since there were a few people that said things weren't cleared up last Tuesday, you can be more specific about what they weren't able to clarify. Who showed up last Tuesday of the student assistants? There's 4 student assistants. I want to see who's been working.
All of them.
All of them showed up. Oh, that's good. Good. Okay. All right. Questions on the problem homework 1? And don't Don't worry about anything being. Okay. By the way, I used the same problem in India at this oil company was having some advanced training on PVT, and because I think it actually was when I started looking at it and reviewing it, I actually liked the problem quite a bit in terms of being able to try to use something quantitative to talk about something as hand waving as is it an oil or a gas reservoir. Generally speaking, it's not easy to use quantitative measures to do that. And so I think that first homework problem did about as good a job as you can do in trying to use quantitative measure of what's the reservoir gas and what's reservoir oil. And it's a little bit non-intuitive, I think, the problem itself. So, yeah. Any questions? Move on from that problem. Okay. How many reissued your solution formally? Okay. I won't ask how many needed to reissue formally. The second homework problem, as you saw in the description, there's going to be emphasis. It's pass-fail. So if you don't pass, then you don't go to the exam, unless you, I guess, resubmit or something. Is going to grade also your Excel communication skills, how well you communicate using Excel in the solution.
In the Excel etiquette video, there was like a note that summarized what we have to do in terms of, let's say, the font size and
Well,
the
don't
list.
have to do.
I mean, a list of the
Recommendations.
optional recommendations.
Yeah, recommendations.
Can we get that note because it's only in the video? We don't see it in the
Oh,
notes.
goodness. That's possible. What's the note called? Let's see here. That probably would be on. That's on here. This first one?
Yeah.
Okay. Let's see if I can find it here.
This has a good summary of the recommendations.
Okay. And then etiquette. I spell it. Obviously, I don't know how to spell it. And then that would be was it a PowerPoint or
No.
PDF? This looks like notes. Those are probably already out there. Here we go. Does this look like it?
Yeah.
Okay, found it. Huh. All right, that's kind of miraculous. Let's see here. So then, is this here, I think? Okay. Yeah. Okay, so you're gonna be you're not going to be this is like not 1984. Anybody know what 1984 means? There's a book called 1984 by Orson Welles, I think. It's about when the government kind of sees and knows everything about you, so you kind of like no longer. So, and one of the most famous Super Bowl. Anybody watch the Super Bowl? There we go. I was on a plane, so I was kind of halfway depressed. I didn't really care who won, but my team, the team that I wanted to win, they lost. So much for that. So one of the most famous Super Bowl commercials is, I think it got within the top 10, maybe within the top 5 rankings of all 50 commercials, was won by Apple Computer. after Steve Jobs returned, after having been fired. So if you can go on the internet, you can look YouTube, and I'm sure it's the commercial from, it's called 1984. Apple, I'm sure you can we could probably pull it up here. But I'm not an Apple kind of guy, so I'm not going to promote that. But anyway, it's not like we're going to enforce you to use 16-point fonts, and if you don't, then you're going to like not go to the exam. But if you use default Bill Gates Excel fonts on your exercise, it probably won't pass, because basically you can't copy and paste that kind of figure into a Word document or a PowerPoint document and be visible. And in other words, the people looking at your presentation or reading your report will not be able to read the text, essentially, because I think the default font's something like 8-point, and it's just too small. So you're going to have to, basically go through the exercise of changing the font sizes to at least absolute minimum, probably 12, but 14 to 16 is what I use. And if you use 16, then you can use the figure both for Word documents and for PowerPoint documents, which you'll be making the rest of your lives. So you might as well get started. If you use 14-point, it may be a little bit small for a PowerPoint presentation in a big auditorium. So it's kind of like safest to go with 16-point. And then in addition to doing the Excel part right, you have to also do the calculations right, which, small details. So I think this homework problem 2 is related to flash calculations, estimating k-values to do flash calculations. Does it include a separator test calculation where you calculate volumes of the moles that become gas and oil? Is that included? Okay. So it's kind of got all the essence of flash calculations. And I will remind you that the first SPE, the first paper within the Society of Petroleum Engineers, which is mother's organization, is called AIME, the American Institute of Metallurgical Engineers, I think. AIME. The first publication within the SPE, the petroleum arm of the AIME, on using a computer was specifically to do the kind of calculations you guys are doing in Excel. And that computer cost probably many annual salaries, maybe the annual salary of the president or more at that time. And it was the size of, probably it would have, this whole area down here would have been with all of the elements making up this computer. So it was a big deal. But the reason they were doing the calculations was important, since that happened to be the first example of using a computer. And why would you do it? Because it's directly impacting the volumes of oil out of a produced well stream. And the volumes of oil, of course, back then, 1949, the value of gas was essentially nil, and the value of oil, although not great, because I know my dad, when he was involved in the oil business in the 1950s, when he first started producing oil, the price of oil was about $2 a barrel. So, but the oil was a lot more valuable than the gas, and anything you could do to get some of the molecules to be in the oil phase was making money. So it is an important exercise.
It included only single stage.
Okay, so single stage flash. So it didn't try to optimize, but of course, it doesn't take too much for you to extend that to a two-stage flash if you're interested in trying to study the impact of the first stage pressure and temperature on trying to maximize the amount of oil produced. So that would be a natural extension that you might do yourself. And then in your first job interview, you can tell them, well, which course did you like best? You can say, well, Curtis's course. Why did you like that? Well, because he gave us the opportunity to do things that were important and didn't have to tell us what to do. Oh, what's that? Well, and then you can tell them the story of the 1949, and you can say, and I actually did this two-stage separator calculation and maximized the amount of oil. you'll get the job. Goddamn, you'll get the job. After you erase that part, you'll probably get the job. Okay, but you should do it. You shouldn't just tell them you did it. You know, so because they may ask you to actually show them what they. So that's your opportunity. And in today's market, you're going to have to do anything and everything you can to separate you from the rest of your buddies to get a job, in addition to good grades. So, questions about doing the flash calculations, estimating K values, anything else about this homework problem 2? Yeah.
For the density of the oil, for the calculation of the density of oil, we calculated it by using the density of each component, and then we take the weighted average with the mole fraction and the molecular weight. So why can't we just take the weighted fraction with the mole fraction only, and why are we including molecular weight?
Okay, so this is a very good question. I was actually, by chance, today asked by one of the other professors in the department who was doing process type calculations for another course, how, for example, like HYSYS, a software program, is calculating the oil volumes in that software. So the question here, this is related to homework problem 2, is how to compute or calculate surface oil volume from the flash calculated oil molar composition. Is that correct? The question? Yeah. And why was it calculated in a certain way? Okay. So the deal is that if you have an oil at standard conditions, okay, an oil at standard conditions is primarily consisting of measurable amounts of like probably C4 and heavier. It's got a little bit of C3, C2, C1, but not very much. So any oil at standard conditions, basically, its volume is, for practical purposes, the sum of the volumes of all of its components. Okay? So basically you can use what's called ideal volume mixing. At least that's what I call it. Ideal volume mixing. And basically it says, and it generally would be very accurate within less than probably a fraction of a percent for oils at standard conditions. Basically oil is any hydrocarbon mixture. Is what I'm going to call an oil. And as an example, if you've got gasoline and diesel, for example, and you've got a liter of each of these by themselves. Now, of course, gasoline and diesel consist of lots of different components. But if we just consider gasoline and diesel as two components, then the sum of the mixture of these two individual liters of gasoline and diesel will be very close to 2 liters. I mean, like as close as you can get measuring. All right? The mass of these 2 liters will be different because the density of gasoline and diesel are different. But the sum of the masses will exactly be, the total mass will be exactly the sum of the 2 masses. There's no assumptions on that. So the total mass is just the sum of the masses, right? We can't get away from that. But the sum of the volumes of 1 liter plus 1 liter being 2 liters, that's a good assumption, very good assumption for hydrocarbon liquids made up of hydrocarbons. It is not a good assumption for all liquids. And of course, all of the alcohol drinking people in this auditorium know that, because if you take a liter of vodka and a liter of water, you don't get 2 liters of mixture. Okay? I'm not sure if you get less or more. You just don't get 2 liters, probably less. And that's because the molecules of alcohol and H2O, they combine in a way that kind of like they make up. Is it less volume or more volume? I never made the measurement. I think it's less. So these are non-ideal liquids, and you can't. They don't have additive. Sometimes this is called additive mixing rule. Okay. So ideal volume mixing basically says that the sum of the volumes of all the components is very closely equal to the total volume after mixing the individual components. Okay? So, in terms of an equation, density of this surface oil is the sum of the masses over the sum of the volumes. And I'm going to put this as, I'm going to write this as, try to write this as, this is at standard conditions of the liquid volumes at standard conditions. I'll put the little bar on top of it to indicate that it's at standard conditions of all the different components. And what we know is the mole fraction, okay? But we also know the molecular weight of each of these, right? Because I think it was given, I mean, we know it for C3 and C4, but for C7 plus in the problem, it was given the molecular weight. So the mass is just, the mass is equal to the moles, which I'm just saying is mole fraction if you have 1 mole, times what? Molecular weight, because that's kilograms per kilomole. So that's just the mole fraction times molecular weight. Apologize for this bad writing. I've got a bad pen here. And the volumes of ideal liquid is the mass of each component divided by its density, right? The mass over the density is the volume. Okay, so that's the sum of the mass, which is xi mi, over the density of standard condition liquid for each component. All right? That's under the assumption that this ideal volume mixing works. So this would not work for alcohol and water. That's why we use this. Okay? And if you just added, if you just did the sum of, I'm not sure you were thinking mole fraction times density, for example. Okay, this is not equal to, or this is not the same as the mole fraction of xi li. Okay? Now, this is not a stupid question. It's a stupid question if you're some really smart person who knows all this stuff. How many knew the rule from when your childhood or through college about additive ideal volume mixing? I mean, how many really understood and knew this? You knew it? Okay. Well, when I was your age and I came to Norway in 1978, was 21 years old. Actually, it was a couple years later I wrote, I think the first paper I wrote in 1980. In that first draft of the paper, which kind of became a fairly known paper, in that paper, I wrote the second equation, something like that. It was wrong, what I wrote, to calculate the average density of a liquid. Now, why they didn't just reject the paper and think this guy's an idiot, why is he writing a paper? It's because the other stuff in the paper hopefully compensated for not being right on that, okay? So there's nothing wrong with you not knowing, and certainly nothing wrong with you not, to ask is a good reason, but it's really very simple, and it's just that we don't necessarily learn that in our chemistry class because chemistry class is not talking often about something that's very practical. They probably told you about alcohol and water not being additive. That they probably told you about because it's interesting, but they might not have said that for hydrocarbons that in fact it is additive. So now you guys know. So it was a very good question, and And so this is the correct way to go about it. And these densities of the liquids, these are in the appendix A for the pure components, or they're measured in basically for the lab by the lab for C7 and heavier. Now C6 is a mixture of several isomers, but the densities of all those isomers, we don't include benzene in the C6, what we call C6. But the other C6s have similar densities. Okay? So they're probably the C6 in Appendix A for pure compounds. And for C6, you can either use Table 5 2, cat sphere is a body, or you could probably get away just using normal C6. Probably good enough. Because all of the C6 isomers are alkanes, I think. Now, this is since we're doing like Casual Tuesday, that's what Casual Tuesday, I'm not really completely here. I'm still seeing elephants and monkeys and strange things like in Taj Mahal and stuff. I mean, I'm still not quite back home yet, so we're doing Casual Tuesday. Okay, let me tell you this story first. You just don't hope you. There's a bigger chance I'll forget the story than I'll forget the question. So I'll just tell you a little bit of historical on this ideal volume mixing. So in the 1940s and 50s, to calculate the oil density or the density of an oil at high pressure and temperature was a big deal. We didn't really have a method to do that. Okay? In the 40s and 50s. By the way, they were doing engineering back then, and they needed oil densities, and they might have oil compositions, and they want to know how to get the oil density at a pressure higher than atmospheric, where ideal volume mixing doesn't work. So at separator conditions or at reservoir conditions, and so Standing and Katz, his advisor, they published a paper, and I don't remember the year, but it was sometime in the 40s. And this, I think, was the second part of his PhD. They gave a method to estimate the density of an oil at pressure and temperature. It's called the Standing-Katz oil density method, and it was what was used from the 40s until, and actually was used beyond then, back in around I think around the 1960s. You had a paper by Elaney and Kennedy. I'm not sure about the spelling there. One of the Texas universities. They gave a more rigorous kind of method of doing the calculation with a cubic equation of state by our friend in the Netherlands, van der Waals. Okay? Van der Waals cubic equation of state, which has two constants for every component, AI and BI, and they gave basically these components AI and BI for all the components in an oil mixture as a function of temperature. Okay? Well, nobody really used this Elaney Kennedy much. It was fairly accurate, but it was more complicated to program, and not until around 1980 did we have these calculators that were robust enough to program, and then we started using computers. So basically this method survived almost 4 decades until around the 1980s, when cubic equations of state that are used today became standard. So this Standing-Katz method was used for about 4 decades. Okay? And that method, that Standing-Katz method, basically is based on the extension of this ideal volume mixing. That's something that could be done on a 13-column pad. That's the predecessor to the Excel Ragnar. In the old days, you had a pad with columns. 13 columns. They call it a 13-column pad. All of the people who do taxes and stuff, engineers, everybody used 13-column pads. Okay, 13 columns. And you could do this calculation in a nice 13-column pad. And it was an extension of this ideal volume mixing at pressure and temperature above standard conditions. So the problem was you can't use it directly. So what you did, I'll just give you kind of the three-step procedure, is that you took and you calculated, you used this equation above that I gave you with ideal standard condition liquid densities. You first calculated that. So you calculated it was kind of the pseudo, they called it pseudo, pseudo oil density. Because you might have 40 mole percent methane, okay, 40 mole percent methane in your oil. And methane doesn't behave like a liquid at standard conditions. So what is its liquid density, okay? Okay. But that includes light components, which was basically methane, ethane, propane, that were not liquids at standard conditions. Also the non-hydrocarbons. Okay. So what we needed were pseudo liquid densities for these components. Okay? We needed pseudo liquid densities at standard conditions. In other words, if methane is 40 mole percent inside an oil, what contribution of volume does it give to the whole oil? That's what you needed to know. You kind of needed to know that. And it's some kind of a pseudo liquid density of methane. Okay? So basically, Standing and Katz came up with pseudo for methane and pseudo, because these were the main gaseous components, okay, for these two components to use in this calculation. Okay? And it kind of gave a, I don't know, it's kind of a strange thing, but these, and these were functions of how much methane was in the oil. Okay? So it was kind of an algorithm. If you look in Chapter 3, it's all discussed, and then in Appendix B, there's actually calculations using this method. You don't need to know it. I'm giving you a history lesson now. So, okay, the point is that they used the same procedure, but they needed estimates of what these two components did to the total volume. Okay? So this got them a pseudo liquid density, but that's at standard conditions. And then the second thing they did was to say that this was a liquid mixture at standard conditions. If we had something that truly was liquid at standard conditions, there were corrections for thermal expansion and compressibility in the literature. I mean, because like based on, liquids, hydrocarbon liquids that actually were liquid at standard conditions, if you wanted to know what a jet fuel liquid volume would change, how its density changed, if you went to high pressure inside, I don't know, jet fuels, maybe they keep them at 5 bar inside the plane. So at 5 bar, how much does the volume change of a jet fuel, 1 liter of jet fuel, at 1 bar up to 5 bar? There was equations and tables for that. Compressibility effect. Okay, what if that jet fuel got real hot? I don't know why you don't want it getting hot, but what would happen if it got real hot? It went to 100 degrees C. what would be the density of that jet fuel. Okay, and there were tables and accurate equations to give the thermal expansion or contraction of a hydrocarbon liquid. So basically, you had standard out of the standard book tables and equations for hydrocarbons. For hydrocarbon liquid thermal and thermal expansion from standard temperature of about 60 degrees Fahrenheit. If you went to any other temperature, higher or lower, you could estimate what its density did at 1 atmosphere. And then you also had the compressibility effect if you went from, for example, 1 atmosphere to 5 atmospheres or 50 or 500 atmospheres. Okay? These were pre-existing correlations, and they said, oh, just use those. And with this two-step process, a simple application of this equation here, simple equation there, where you had to estimate, and this was probably the most important part of the correlation of standing in cats, what do I use for methane and ethane, the pseudo-liquid densities, to come up with the pseudo-liquid density of the mixture and then make these standard corrections. And one could do this in an hour or two on a 13-column pad. And then you're done, you get the density. Okay? So the method was extended to high pressures and high temperatures in a relatively accurate way. And you got densities within a couple of percent. Okay? So this method in general leads to accuracies probably better than 2% for most oils. That's pretty damn good.
So does the compressibility effect take care of having the methane and ethane?
Yeah, because the way they developed the whole correlation was that it takes care of it as if it was just any old liquid with the density, a stock tank liquid density of 0.6. It would have certain compressibility effects, and yeah. So these tables and figures, these are they don't need to know how much methane and ethane are there. Okay, they basically are a function of the pseudo oil density. Okay, so if that pseudo oil density is low, then it's got a higher compressibility. Okay, so it's dependent on the density of the material. So anyway, this is now. So that's 2. This is in petroleum engineering. That's what we used for about 4 decades. I realize that you don't really care. Nobody uses it today, not even in programs that do simplified calculations. It's basically the method's dead now, for the most part. However, I will make a comment that in the process industry, your chemical engineering friends, okay, when they do calculations at separator conditions, which is what we're kind of doing now, in the process industry, they still, for the most part, they still use empirical oil density as a function of pressure, temperature, and composition methods developed in, I think it was the 1960s. The guy who originally came up, the method that's used mostly is referred to as Kusol. Okay, it was originally published by a guy at Phillips Petroleum Company, Hankinson, maybe some other authors, and then it was generalized by the, I think ASTM or the API, I don't really know. It was generalized APM some organization into what's now called COSTEL. Okay, it's kind of I don't know what they did to it, but manipulate it. They don't call it the Hankinson method anymore, but that's essentially what it is. And it does something a little bit different than the standing cats. It's no more accurate than that, but so the process industry still uses empirical methods. And you can look this up on the internet and find how the method works if you've got composition, pressure, and temperature. And this is about the same accuracy as the standing cats. You know, probably within a couple % accuracy. Okay? So that's a long question to a long answer to a short question, but you got some history out of it. What was your second question before we go to lunch?
Yeah, second question is about the K values.
Yeah.
So, like for example, at convergence pressure, we get all components get the K value is equal to 1.
Okay. Convergence pressure, we don't have time to before the break. So right after the break, we'll take that question. Okay, so we'll take a 15-minute break.